Hey there. So I changed my mind. At the end of the last video, I said I was going to continue on with the stock Monte Carlo linear systems thing and expand that, describe how to do the matrix manipulation for that for multiple stock runs. But I think I'm going to do the partial differential equations first. So what we're going to do is look at heat transfer in one dimension. So we're going to have a partial differential equation, partial derivatives with respect to both time and spatial variables that give the temperature. And since there are really no partial differential equation solvers, I mean, there's finite element stuff, but that's kind of slow and overkill for this problem. So what we're going to do is transform that into a system of ordinary differential equations, and there are ODE solvers available for Python. So we're going to end up with a fairly large system of equations. In this case, I think we're going to just do like 100 grid points. So we'll end up with like 100, 99, 100 differential equations and a couple boundary constraints. So I will write some code to show you how to do that using matrix manipulation to generate our system of equations. And I'll also do it using a for loop, and you're going to see a huge difference in the performance. And I think this gives a better indication of why you'd want to use this type of matrix manipulation than the stock Monte Carlo ones, since that's not that computationally intensive, and this is more so. So you're going to see quite a difference in performance, even though we don't really do anything complicated. We don't even like invert a matrix. We just use matrix multiplication to come up with our system of equations. So let's just dive into it. Dive into a notebook, and we will describe the problem. So here's the problem we're going to look at. We're going to take a long, thin rod of 1 unit of length. I think I took it to be meters, but you can use whatever system of units you want. So 1 meter long, initially all at 20 degrees Celsius, and then we put one end in contact with a fixed temperature source. We're basically going to fix the temperature at one end to be 0, the temperature at the other end to be 30, and ask what is the temperature of the rod as a function of both time and position along the rod. So here's the equation that actually describes that. It's a partial differential equation. Capital T will be the temperature, little t will be the time, x will be the position along the x-axis. And what we have is this. Some constant, diffusion constant times the second derivative of the temperature with respect to position is equal to the time derivative of the temperature. So we have two different derivatives with respect to two different variables here, and then we have some boundary conditions here. Now, since we're going to solve this with an ordinary differential equation solver, and the way we're going to do that is to come up with an approximation for this term here, the second derivative of temperature with respect to space. And so we're going to discretize that, and we're going to end up with a whole bunch of equations that give the time derivative at a particular point along the rod. So we're going to end up with a very large system of ordinary differential equations, first order differential equations in time only. So this is the approximation we're going to make. We're going to break our spatial domain into a bunch of grid points with a spacing delta x, and we're going to approximate the second derivative as some sort of difference formula. So it's going to be equal to this term here. This is the second derivative is approximately equal to t at the ith plus 1 point minus 2t at the ith point plus t at the I minus 1 point. So that's our approximation for the second derivative. And what this is going to do is transform our system from this, a partial differential equation, into a whole bunch of ordinary differential equations with a couple boundary constraints, which I've shown here. So t at the 0th point at the left end, I believe I said it was equal to, no, I said it was equal to 0. Let me change that. 0. So t at the left end is equal to 0, and then we have our first differential equation, t at the second point minus t at the first point, which we're interested in, minus t at this 0th point, which is equal to 0, gives this equation, and so on. So we have a whole bunch of ordinary differential equations, and then at the last point is some, if you chop it up into n points, the temperature at the nth point is our other boundary condition, which in this case was 30 degrees. Okay, the way I think I'm going to set up this video is obviously these equations here, we could iterate over them to build this system of equations just using a for loop. And I think that's how I'm going to actually structure the video at first. So I'm going to build this system here with a for loop and then talk about how it generalizes to more dimensions, and then show that obviously this is going to become problematic very quickly. And then move on to the matrix representation. So let's just start with the for loop. What I'm going to do here is do my imports now. We're going to be using the assimilo package again, which we've talked about before, to do the actual integration of the differential equations. We're going to eventually need the sparse diagonal command from the Scipy sparse package. And just to do some comparisons, I'm going to import time as well. So let me do that. Okay, let us now move on, and I'm going to turn off the camera here. Okay, let's go. Since we can't pass additional arguments to the solver, I'm just going to wrap everything in a class, and we've done this before. We've talked about assimilo in the past. D is going to be equal to 10 to the minus 4. That's our diffusion constant. And our number of grid points, I'm just going to set to 101. So there are 101 grid points and 100 individual divisions between them. So we're going to build our constructor. Okay, we're going to need some sort of time span to do the integration over, and I'm just going to take that to be 6,000 seconds, presumably. And we're going to need to set our vector of initial conditions. So that is going to be initially np dot, we could do this as np dot ones. We could do n of those, and since the initial temperature of the rod is 20, we will multiply this by 20. Let's come down here. Let's set the initial element equal to 0, so that's our boundary condition, and we will set the last element equal to 30, which is our other boundary condition. Let's see if this actually takes this. There is a typo. There we go. Okay, let's continue to build this up. We're going to also need to pass an initial time to the solver. So let's do that up here and just say t0 is equal to 0. So we'll start at the clock at 0. And I think before moving on to the solver calls, I will define the equation system here. So let's just create a function called equation system. It's going to take the arguments little t for time. It's going to require capital T, which is our temperature vector. It's going to take t prime, which is the time derivative of the temperature vector, and it's going to the solver requires this variable SW, which we're not going to use, but it needs to be there anyways. Okay, so the solver assumes that this equation system is equal to 0. So we need to construct our residual vector. I'll call it res, and that's going to be equal to np dot zeros, and we'll just make it the same shape as our temperature vector, so t shape. Okay, so now I'm going to set up the first boundary condition. So the first element of that residual array is equal to, well, it has to be equal to 0, but this equation up here is this. So it's our temperature at that boundary, which happens to be equal to 0. So what I'm going to do, I'm going to be very explicit about it here, just so there's no ambiguity, and say the temperature at that grid point minus is equal to the boundary condition. So obviously, if this were a 10, if that boundary were actually 10 degrees, this equation obviously would return zero, because this, what's going to happen is it's going to force this residual to be 0. So our unknown here is our temperature, and our temperature minus 10 is 0. In other words, our temperature would be 10. But our initial condition was 0. Maybe I should have chosen a better initial condition there. So our last element in the array is our boundary condition. So res minus 1 is equal to t minus 1. And that we have to subtract off that other boundary condition, which is 30 degrees. So now we need to fill out this internal part. So for I in range, we want this to start at 1 this time, not 0, because we've already defined our 0th element up here. And we want it to go to the number of elements in t. So t dot size. And now we're going to set our ith element of our residual vector, and that's equal to. We're also going to need, before we do that, we need to do our grid spacing. So let's call our grid spacing delta, and we'll set that equal to 1.0 divided by the number of elements, the number of grid points minus 1. So divided by self dot n minus 1. That should give the spacing between each of our grid points. And now we can come down here. Where am I? Here I am. This is going to be equal to our t prime, so our temperature derivative at the ith point. Now this whole thing has to, ith point, there we go. This whole thing has to equal 0. So we're going to subtract off. What we're basically doing is moving this difference equation to this side of here. So we're having our temperature derivative minus this term here is equal to 0. So we need to code up this term here. So that's going to be equal to d, our diffusion constant, that's self.d, is it not? Self.d divided by, come on, self.d, at least I caught it. You know how I tend to make mistakes here, and it would take me an hour to find it otherwise. So self.d divided by delta, and that is equal to t I plus 1 minus 2 times t I plus t I minus 1. And that looks, actually there should be delta squared, should it not? Delta squared. Yes, delta squared. Okay, now return res. Typo. Do I have too many brackets here? Another typo. Oh, res minus 1. There we go. So now let's come up here and actually build the solver or call our solver on this function down here. We need to pass in a t prime vector. So let's come up here and just say t prime is equal to np.zeros. We don't know this. We're going to have to solve for it, but we need an initial guess. So np.zeros, and it's going to be the same size as t. So t dot shape. That should do it. We're going to need this switch variable here. Again, it's not used, so I'm just going to set sw. Sw is equal to, it's a Boolean vector, so what I'm going to do is just do t dot size times false. So basically it's just going to create 101 false false entries there for it. Oops. False. Let's just see. Okay. Our algebraic variable thing. I'm going through this very quickly because we've talked about assimilar before in differential algebraic equations. So this is just all the boilerplate we kind of need to get the thing going. But we do need to reset the 0th element to false here, and the last element is also false. So these are our two algebraic equations. Let's just make sure it takes it. Cool. So now we need to create a model object. So we do that here with this implicit problem which we imported earlier. Now we need to create a simulation object. And we're using IDA out of sundials. Again, I talked about this in previous videos, so I'm not going to really dwell on it here. Our model. And now we need to pass in some of our parameters to our simulation object. And because we're not doing anything fancy, that only needs to be the algebraic variable thing here. We call our find consistent initial conditions function, and we are ready to actually do the integration. So let's come down here. Our solver is going to return time, our temperature, capital T, and T prime, and that's going to be equal to sim.simulate. Can I simulate our T-span object, or our T-span number, and I'm just going to ask for 500 integration points. And let's just make these output variables class variables, so we have access to them outside of the class. Self.t, self.capt, and self.t prime. So hopefully this will work. And let's come down here and actually try it out. So we can create an instance of this class. Let's call it problem underscore loop. And that is equal to our diffusion class here. And let's just see if it runs. Nope. Where's my init? I need a self in here, don't I? Self. And now we have a typo here. N is not defined. That's because it's a self.n. Where is it? Where is it? Where is it? Self.n. Oh, it's up here. Self.n. That should do it. One more problem, T0 is not defined. That's probably because I just called it T up here. Yes, I called it T up here, so T. T0 is not defined. How can that be? Oh, I called it T and T prime. Damn it. Same mistake twice in a row. And little t0. Okay. The solver failed. T prime is not defined. T prime. Still no? No, what's going on? Index 101 is out of bounds. Oh, it's getting to the end here. I'm trying to go beyond the end of the array because of this +1 down here. So this should be t size -1. There we go. Now let's wrap this in code to figure out how long it actually takes to run. So I'm going to say start is equal to time, end is equal to time, print time is equal to end minus start. So it takes 0.65 seconds. Let's just plot out our answers to make sure it makes sense and just play around with some of the time steps to make sure this is a reasonable result. So I'm going to create a spatial variable x, and now we're ready to go plt.plot x comma problem.loop underscore loop. We want our temperature array. Let's just plot it out initially before the actual time starts to run. So time equal to 0. So the 0th row, all columns. That should do it. Let's plot it. What's going on? Problem is not defined, huh? Oh, problem underscore loop. So that's what we said the temperature was at the beginning. It's 20 degrees everywhere except for our fixed boundary conditions. Let's just try to advance this through through time. So like 100 time steps into the future. It's almost completely linear. Let's back it off a little bit. Go 50 time steps into the future. So you see what's happening. It's getting more and more linear as time goes on. So if we go all the way to our last time step, it should be almost perfectly linear, which it is. And our midpoint temperature is about 15 degrees, which is what you'd expect. You'd expect it to be the average of the two temperature extremes on either side. Cool. So, I'm not going to talk about the 2D problem right now, but suffice it to say, when you double the number of dimensions, you essentially square the number of elements in your temperature array and your all these things here. So this would end up being 10,000 plus differential equations instead of 100. So let's just come up here and see how long it would take to run. If we set our number, can't find my cursor here, glare off of the screen. Instead of 101, let's just make this 10,001 and see how long this takes to run. Okay, so after an hour, I shut this down, and instead of 10,000, I cut the number down to what, 1,001. And it still took over 80 seconds to do it with 1,000 points. So this problem kind of blows up exponentially, and you can't solve it, so it doesn't scale well. Imagine doing a three-dimensional problem. So instead of 100 by 100, it would be 1,000,000 by 1,000,000. It just wouldn't be possible. However, as you could tell, since the theme of these last few videos is how to recast these in terms of matrices, we can write this as a system. We could write this system of equations as a single matrix equation and take advantage of sparsity to get around that problem. So what I'm going to do before I forget is set this back to 100. And now how can we write this as a matrix? So again, I'm going to turn off the camera. And let's move down here. Okay, so you may have to stare at this, and I apologize if these don't really scale that well, but there's fractions in this that kind of screw things up in terms of like the vertical scaling on the screen. But hopefully you can convince yourself that this matrix equation is the same as this system. Where is it? All the way up here. So let's go back down here and just kind of think through this. This first line should be pretty obvious. All of these are zeros except for this value here, which is 1. So we just pick off this t1. Our first derivative at the first point with respect to time is equal to what? It's equal to t0 minus 2t2, t1, I'm sorry, minus or plus t1, and then everything else is 0. Oh, and I forgot the let me write these, the delta and the diffusion constant. Let me write those in. Shut off the recording and write those in. So there we go. So if we multiply through this line here, we get t0 minus 2t1 plus t2 times this, which is the same as that first equation. Where is it? Right up here. And so on for all the others. Now again, the theme of these series of videos is this matrix is sparse. In fact, it's what's called the tridiagonal matrix. There are only non-zero entries on the main diagonal and the ones immediately above and below that. So we can use this to speed up our calculation immensely. So let's code up this problem down here, taking advantage of this. Okay, since 90% of this is going to be the same, I'm just going to copy this entire class down here and just make some edits to it. So I'm going to paste it in. I'm going to change it from diffusion loop to diffusion matrix. And what we're going to need to do is change this function down here. So I'm going to get rid of that. Just as in the previous video, we are going to use the sparse diags command to create this matrix. So our off diagonal terms are going to be 1 and 1. Our main diagonal is going to be the -2. Here's our positions, one diagonal below, main diagonal, one above, and the shape is the same, is t dot size, so it's a square matrix. And that's about it. We can now create our residual vector. We don't even need this line up here anymore. We'll keep it. Okay. So our residual vector is going to be equal, just as before, to t prime minus self.d, the diffusion coefficient, divided by that delta squared. So delta squared. And it's just going to be multiplied times this matrix M. And then we have to put in our temperature vector, and that's it. Now we just need to set the initial conditions. So our initial temperature, our res 0, is equal to T0 minus 0. What's wrong here? What the hell happened here? Res 0 is equal to T0 minus 0, and res, the last element, minus 1 element, is equal to T minus 1, and that is equal to 30 degrees. That should be it. Let's just see if there are any typos. Of course there are. Okay, fixed. So hopefully we can just come up here again and steal this code. So I'm just going to select all, copy, paste, and this is no longer diffusion loop but diffusion matrix. Let's just see if it actually runs. Excellent, and it runs in a fraction of a second. So let's just plot that out to make sure we're good to go. So again, we're just going to come up here and steal that, paste it in. Looks about the same. Let's just see. Our initial conditions look okay. 10 time steps in, looks reasonable. So, come on. Okay, now let's come up here to our matrix code and change this to 10,001. Run. Okay, we've finished. I've edited this for time, obviously, but we have 235 seconds as opposed to not finishing within an hour plus for the other case. So, vast difference between the two. Okay, so I'm going to call it quits for this particular video and move on to part 3, where we go back to the Monte Carlo techniques. I know I glossed over an awful lot in here. I didn't really speak in detail about partial differential equations and how we, I didn't draw out any schematics of how we did the discretization and things like that. And I know I've talked about sundials in the past, but I've glossed over an awful lot of the things we've done here. So I may kind of repeat this video in the future, but focusing more on the physics and the solvers that we're using here. So this was essentially just a demonstration of the fact that we're not making things just needlessly complex by using these matrix equations. You speed up the calculations immensely. You cut down immensely on your memory usage and things like that. So there is a method to my madness and a point to all of this. So yeah, next video coming soon. We'll go back to the Monte Carlo method, as I said, and go through that in more detail. So until then, see ya.